In this section, we would be studying about the gaseous laws. Now let's first understand what we mean by the gaseous laws. Gaseous laws are basically statements which relate the parameters of a gas. And if you try to remember, in the previous section we had studied that the gaseous parameters are temperature, pressure, volume, and the number of moles. So basically, in the gaseous laws, we would hold some of these as constants and derive relationships between the other parameters. So the first gaseous law is the Boyle's law. Okay. At constant temperature, our first parameter out of pressure, volume, temperature, and number of moles, the temperature is constant. Pressure of a certain amount of gas. Now, by a certain amount, we mean certain number of moles. So the number of moles also becomes fixed. The pressure varies inversely with the volume occupied by the gas. So the relationship, if written in mathematical terms, comes out to be P is inversely proportional to V. And to remove this proportionality, we introduce a constant of proportionality. And so our equation can also be written as PV is equal to K. And from this, we derive one thing, that when the temperature and number of moles of a gas are given to be constant, we can say that the pressure in state 1 times the volume in state 1 will be equal to the pressure in state 2 times the volume in state 2 will be equal to the pressure in state 3 times the volume in state 3, and so on. So this is basically what the Boyle's law is. Now, various graphs can be plotted at different values of temperature, keeping the temperature constant along a particular graph between the parameters pressure and volume. So let's just plot the first graph, which is between pressure and volume, with pressure being on the y-axis. So if we look at this equation can give us a feel as to how the graph should look. Now we have not actually seen any such kind of equation before. So we'll plot this analytically. See, when pressure goes to infinity, right, that is this part of the graph, the volume should go to 0 for the left hand side to be equal to the right hand side, right? So when pressure is infinity, that is this part, the volume has to be near 0. So this can be said to be one of the points on the graph. And similarly, when pressure goes to 0, the volume should go to infinity for it to be a viable equation. And remember, here the constant of proportionality K is a non-zero constant and is finite. It does not go to infinity. So when pressure is 0, that is this part in the graph, the volume goes to infinity. So this can be said as another point. And when various such points are plotted, they actually take the shape of a rectangular hyperbola. So various such hyperbolas can be plotted. Now, one thing which has to be noted is that for a rectangular hyperbola, this point, which is the point along the y is equal to x line, okay, this point is something which is the closest and is a measure of the temperature. So as we go farther away on this line, increases. So let's say this one is plotted at T1, this at T2, and this at T3. Then T3 is greater than T2 is greater than T1. Next, we have the pressure versus 1 by V graph. So for this, we can directly refer to this equation, and for our ease, rewrite it as P is equal to K times 1 by V. Or just write it as y, as p is on the y-axis, is equal to k times x, as x is on the x-axis, right? 1 by v. So we can say that the graph would have a slope of k and would pass through the origin. However, if you look carefully, passing through the origin, that is p is equal to 0 and v is equal to 0, would mean that the quantity on the x-axis is also 0. And if we look carefully, the quantity on the x-axis is 1 by v. 1 by v is equal to 0 would imply that v has gone to infinity, which is not practically possible. So we do not actually pass the graph through the origin but interpolate it. Let's look at what we have. The graphs would look something of this sort, right? Something this sort of different slopes which are k. And when traced back, these graphs would pass through the origin, right? So these graphs would be at different values of temperature. So the higher the slope, the higher would be the temperature. So again, we'll use the same relation that T3 is greater than T2 is greater than T1. Next, we have a curve between PV and V. Now, if you look at this curve, we had said that PV is equal to a constant, right? Right here we had said so. So if PV is equal to a constant, be it any value of V, the graph for PV would go as a straight line and the intercept for this straight line would be K. And similarly, if you talk about the P versus P by V graph, the graph would go as a straight line, but this time parallel to the y-axis. Why? Because PV is on the x-axis and the intercept would again be equal to K. So our basic conclusion for the Boyle's law will be that PV is equal to constant. And this can be written as P is equal to K divided by V. That is, P is inversely proportional to the volume occupied. Now we have the next law, which is the Charles law. The Charles law, which says that at constant pressure, now out of the parameters, pressure is the first one which we've kept as constant. Volume of a fixed amount of gas, now we have fixed the amount as well, varies directly with temperature. Now if we write this in mathematical terms, it can be written that V is proportional to T, or we can write it as V is equal to KT, right? Or another form of writing it is V divided by T is equal to a constant. V divided by T comes out to be a constant. We can say that in a condition where the pressure and number of moles are fixed, V1 divided by T1 in state 1 will be equal to V2 divided by T2 will be equal to V3 divided by T3 and so on. So from this we can plot a few V versus T graphs. Let's look at the first graph, which is simply V versus T, which we get from this equation. That is, the graphs would be straight lines passing through the origin, since the equation is of the form y is equal to mx, which is a straight line equation. Now the slope will be k, right? And on the x-axis we have the temperature and on the y-axis we have the volume. We would have graphs which look like this, right? And these graphs would be at different values of pressure. Let's say this graph is at a value P1, this is at P2, and this is at P3. All these, when interpolated, would pass through the origin. Now, we are not actually drawing these as solid lines because if they actually pass through the origin, like in real, it would mean that the volume is zero. And zero volume has no physical significance, right? It is something which is not possible. Everything has to occupy some volume. Therefore, we just interpolate these because the curves suggest that they should pass through the origin as 0, 0 satisfies this equation. However, it is not physically possible. And here in the pressure curve, we say that P1 is less than P2 is less than P3. That is, higher the pressure, lower would be the slope of the curve. Next, we have a curve between V by T versus V. Now remember, we had said that V by T is a constant. So if it is a constant, be it any value of V, this graph has to come out to be a straight line with the value of the intercept as K. And similarly, V by T versus T, be it any value of T, the graph will have to come out to be a straight line with the intercept as K. So the basic thing which we need to remember for the Charles law will be that V by T is a constant. The next law which we have is the Gay-Lussac's law. Now the Gay-Lussac's law states that at a constant volume, Now out of our parameters, we have fixed the volume. Pressure of a fixed amount of gas, that is, the number of moles has also been fixed, varies directly with temperature. All these laws were generated by scientists after extensive experiments. Okay, so we take them to be true. According to this law, at constant volume, pressure is proportional to temperature. That is, P is directly proportional to T. Or we can write it as P is equal to KT, or P divided by T is equal to K. Now remember that this K is also experimentally found out, or in further cases we'll see that it comes from the ideal gas equation. But for now, take it to be a constant which is found out experimentally by the scientist. So from this, we can conclude that P1 divided by T1 will be equal to P2 divided by T2 will be equal to P3 divided by T3, and so on. So using these relations, we can draw some graphs between pressure and temperature. As you can see that the pressure temperature graph has to be a straight line. And like in the previous cases, at different values of volume, the graph would have different slope, right? Which when interpolated would pass through the origin. But we're not actually passing them through the origin. The reason being that now the temperature is in Kelvin. It is the absolute temperature. Okay. And 0 Kelvin temperature is not attainable. So we are simply interpolating it just because of physical restrictions. And if we call this to be V1, this at V2 and this at V3. Now what does fixed volume mean? A fixed volume would mean that you have kept the gas in a given box which has a fixed volume. It cannot expand or contract. And you are changing the temperature by, let's say, an ice bath around the box, and the pressure inside is also varying. But the box is sealed, the air cannot escape, so the number of moles would also be fixed. And since it is a rigid box, the volume would also be fixed. Okay, so here the volume relation can be written as V1 will be less than V2 will be less than V3. Then we have P by T versus T curve. We had seen that P by T is a constant. So for the P by T versus T curve, it would simply be a straight line with this part equal to K, the intercept. And the P versus P by T will also be a straight line, but this time parallel to the y-axis with the x-intercept being K. So the next law which we have is the Avogadro's law. Now this is a relatively simpler law. If you notice, as yet, out of the 4 parameters which we had always kept n as a constant, right? And had varied pressure, volume and temperature one by one for all the laws. But for the Avogadro's law, what we do is we keep the number of moles as not constant. So this law states that the volume of all gases contained equal number of moles at the same temperature and pressure. Okay, so basically what does this mean? That now we have fixed the pressure and the temperature, and now the number of moles is something which is a variable. So the volume is proportional to the number of moles, and the scientist has framed it this way that equal volumes, say V1, for a gas, let's say we have 3 gases, gas A, gas B and gas C. Gas A is occupying volume V1, gas B is also occupying volume V1, and gas C is also occupying volume V1. So equal volumes of all the gases, although these 3 are different gases with different molecular masses, if kept at the same pressure and the same temperature, all 3 of these would occupy the same number of moles. Okay, this is what the Gay-Lussac's law states, and therefore we can say that V is equal to K times N. So this is something which you should remember from this law.